So as kind of an outline as to what our talk is going to be about, we're going to start with an overview, starting with the work we've done on our network stack and building on top of seL4. And that's going to go into a discussion about our experience. And because we are building a network stack and it's a system level software, most of our experience is with the Microkit and SDDF. And we'll also talk about IPBench, which is a benchmarking software that seL4 used to benchmark its own software. And we'll end off with a little bit of performance characterization of where our stack's currently at via throughput and latency metrics. So what we're striving for, we're designing on top of seL4 with a focus on verification because we feel like a microkernel will bring performance and security benefits to higher level system software. We want to prove the value of this methodology by creating an IPv6 stack targeting fixed function embedded IoT devices. And the device we have envisioned right now is a networked temperature sensor that could be in lab environments. We are using formal methods similar to seL4 to verify our network stack. And we're specifically looking at using Dijkstra's separation of concerns. So our layers are reasoned about separately. And we do this so that if we make changes to one layer, it doesn't make changes and affect all of the other layers. We've chosen to specifically support IPv6 and minimal set of protocols for two main reasons. One, to reduce the proof depth, and two, the adoption of IPv6 is kind of slow. And we really want to increase its usage, especially in embedded systems and embedded devices. And for that last point to really be true, for us to provide a high performance network stack for these sorts of devices, we have to be competitive. And we've specifically looked at LWIP because that's what the SDDF uses, and we want to be competitive with that.
So how did we get here? Well, we're here in part because we've been here for a little while now. We're very excited that this is our third year being here at the summit to share our work with you all. Like Caitlyn mentioned, this project started back in 2021 before the Microkit was even called the Microkit and before official releases of both it and SDDF were available. Around this time last year in Minneapolis, I shared that we had neared completion of all of our network layers, and as sort of a proof of life for our network stack, we had a working ping-like application. Since then, and since official releases of both Microkit and SDDF have come out, we have switched to integrating those into our project. And over the last month or so, we've started collecting some performance metrics of our stack. Last year, I said that we were hoping to release at the end of 2023. Unfortunately, that didn't happen. We're quite a small team, but we are hoping to be able to reach that goal soon. Our team is working on finalizing some licensing decisions.
So on to our experience with seL4, and why did we choose seL4? Well, you're all here. It's obviously the fastest verified microkernel out there. There's no other real choice, at least not on our part. So our lab environment, we had a 10 gigabit network connected to gateway targets and clients, and this all lended itself really well to IPBench testing. And on that same note, we also worked on getting a TFTP server. This is for continuous integration. We're not quite at continuous integration, but that's what we're working towards. And regular benchmarking. We're benchmarking with IPBench, but IPBench doesn't natively support IPv6 testing, so we ported it to IPv6. And we'd love to contribute these ports back to the community when we get the opportunity to do so.
Now we are building on top of the Microkit, and we're using Docker to create a shared build environment across our team. When we started on this project, it was still required that you had to build the SDK yourself, and that did provide a bit of a challenge for our team. It's just extra work having to manage those extra dependencies. So with the official release of Microkit, including pre-built SDKs, it's really been quite easy to integrate that into our Docker container. It's only a couple lines of Docker file, and to stay current with the most recent builds. It's just updating the pointer to that resource. And overall, that's really smoothed out the use of this with our within our project. There have been a couple things that have slowed us down. Keeping up with API changes has been a bit of a challenge, as like I said, we're a small team. But as the API has continued to solidify, this has been less and less of a burden. And as we're writing networking software, we rely very heavily on SDDF for our Ethernet drivers. As far as board support goes, we've been focused primarily on the C2, but have been switching more so to the C4, as that seems to be a bit more in favor amongst the community. And building for different boards certainly is, in my opinion, one of the strong suits of SDDF and the Microkit. Supporting all of these boards is quite easy, and switching back and forth between building for them is a breeze. There have been a couple road bumps for us using SDDF, and a lot of these Yvonne had touched on in his talk earlier today. Kind of plumbing all of the components together can be a bit tricky. The drivers and some of the utilities built into SDDF can be a bit inflexible at times, as they appear to integrate quite well with the included examples, but bringing them into our own project has provided some sticking points. But excited to see how the new tooling Yvonne mentioned earlier today can help smooth out those road bumps going forward. And much like the Microkit, as the APIs have continued to solidify, that's made staying current a lot easier for us. And we've enjoyed seeing the documentation grow. We've been able to reach out multiple times to clarify some questions, and the community has been very responsive.
So for verification, we're writing in C because seL4 has a C parser, and we're using Isabelle HOL to verify a lot of our code, specifically most of the layers, and also the fragmentation and reassembly. We're currently working on verifying the MAC layer, and you can see an example of a proof that we're working on to the right. Where we sort of differ from seL4's methodology is we're also using a little bit of TLA Plus to help inform our distributed protocols implementations. And right now we're using it for queues and neighbor discovery. In general, our experience has had ups and downs. As Wyeth said, we are a small team and our members do constantly cycle. Seniors graduate, life kind of gets in the way, the semester starts. But also because seL4 isn't used everywhere yet, and it's really specifically not taught at our college yet, there's a lot of complexities in onboarding new members where they have to learn how to use seL4 and its tooling before they can actually contribute to our own project. Wyeth also mentioned issues with upkeep, which is expected with the maturing of seL4's tools, and trying to stay current is always a struggle. But again, official releases have made this much easier, and API improvements have made this much easier. And one big bonus is that the community has always been really, really responsive, encouraging, and helpful. We've always been able to ask questions and get plenty of answers.
Now we are talking primarily about our experience today, but to touch a bit on our current performance, we'll talk about that now. Just a very brief overview of what our architecture looks like. Like Caitlyn mentioned, we're really trying to adhere to a strict separation of concerns, and that approach lends itself quite nicely to a networking stack where we have these almost predefined layers to work with and reason about. As far as the actual metrics go, I was really hoping, working hard this summer, to have a nice linear line like we see in Gernot's talk earlier today, which was LWIP on top of STDF and the Microkit. Here we have a comparison between us and a recent build of Ubuntu with a simple Echo server running on it. And unfortunately, our performance starts to plateau at around 200 megabit per second, and we're struggling to achieve some of those higher throughputs. We're hoping with some more analysis of our software and making some more optimizations that we'll be able to reach our performance goals, but we're not quite there yet. And it's the same case, unfortunately, at the moment for our latency results as well. So same comparison here, just focused on round-trip latencies. And again, we're quite competitive up to around that 200 megabit per second mark, and then we start to fall off quite a bit. What you can't really tell from these graphs is before our performance falls off, our round-trip latencies are about half as what they are with Linux. Granted, Linux isn't the end-all, be-all for speed, but we have a ways to go. Anyway, thank you all for being here, taking the time to give us a listen. Thank you especially to all the names up here for helping us along the way.